Swayam Prabha. Digital India. Educated India.
Hello everybody, welcome back to this series of lecture on elements of solar energy conversion. We started looking at the photovoltaic conversion method. We have started with the basics, how the semiconductor, the carrier or the charge carriers concentrations can be tweaked, what are the major factors in quantifying those concentrations, these we have looked at. And at the end of the last class, what we have started is the carrier motion. Okay. So, today we are going to continue on that carrier motion, and then we will introduce few new concepts to understand this carrier motion in more detail. Today we are here at lecture number 30. So, in the last class we have looked at this carrier motion, and this N naught and P naught, these are the equilibrium concentrations. Okay. Now, if this equilibrium is perturbed either by applying a voltage or by putting solar light on these photovoltaic materials, then the equilibrium is perturbed and then the carrier motion becomes real. Okay. So, here we now try to understand what kind of motions are there and what are the factors on which those motions depend on. So, first kind of motion we called it drift motion. Okay. What is drift? Whenever we have some electric field, then these charge carriers, which are charged particles either electron or hole, due to the electric field it will move in directions, okay, and that is called the drift motion. So, if an electric field of strength xi is applied, a carrier, it can be anything, with charge q will feel a force of magnitude F equal to q multiplied by xi, right. So, this is just like Newton's first law. Here the acceleration and mass is replaced by charge and field, okay, and it will accelerate as long as this force is present, right. That is Newton's first law. As long as the force is applied or force is present, it will increase its velocity. Okay. So, for electron, this q is negative, right, and for hole it is positive, is not it? Now, the direction of course will depend on the charge sign, right. So, whether it is positive or negative, that will tell what would be the direction of motion. Now, it will accelerate, but it will be opposed as well, because the charge carriers are not moving in vacuum, right. They are interacting with all the other charge carriers and the atoms in the lattice, right. So, they are constantly colliding with other charge carriers and atoms in the lattice, isn't it? So, by the process, what is happening? They are getting reflected and decelerated by the other carriers atoms etc. present in its path. Okay. So, it is not only just the application of field is introducing a force, it is also allowing the deceleration mechanism. So, ultimately what it will happen, that you can find an average velocity is obtained for certain kind of charge carrier. So, for all the electrons, if you take the average of all these collisions and the field applied field, then what will happen, that you will get an average velocity which is called, let me write this, charge carriers, that average velocity is called drift velocity or V subscripted with D. Okay. And of course, it can change with time. So, there might be some acceleration, net acceleration on average for all the electrons, then you will have an increasing function, increasing drift velocity with time. Okay. Now, if you have that drift velocity, the effect of that on current, so current due to the drift velocity would be, let us say it is I n, I stands for current, n stands for electron, and let us put it drift, because it is drift only current. Okay. Now, it will be q into n into V d into A, and the charge of each electron is minus q, and the current is measured always in the opposite direction of electron. So, there is another minus sign in front. And what are other things? So, these are, this is the number of electrons, this is already drift velocity, okay, and this is the cross sectional area, because we are not talking about current density, but current. So, that will depend on the cross sectional area. Okay. So, this is straightforward. Now, similarly, so now if we put current density, okay, that we represent through the symbol J. So, J n drift will be Q n V d. Two positives make it negative, two negative make it positive, and then you have this drift velocity V d. And similarly, for the holes you can find J p drift, that will again be Q p V d. So, p is the number of holes available. Okay. So, now if V d is plotted, so now we want to know some material property which will tell you the V d, right. So, acceleration is the force is known, that is due to the field, okay, q into xi. Now, the drift velocity will depend on the lattice structure, other carrier concentration and everything. So, it will depend on some material property, right. So, we want to quantify that drift velocity, or we want to relate that drift velocity with the particular material property. Okay. So, to do that, if we plot this V d as a function of applied field, then for initial part, so up to about 1000 volt per centimeter, okay, if that is the field strength, then you will have, for that initial part you will have a linear dependence, just like the stress strain curve. You know, for the initial part you have a linear dependence, and we call that is the elastic part, okay. And beyond, when the stress value or the strain value is higher than certain value, then you have this plastic region where the relationship is not linear anymore. Here also V d, if it is plotted against xi or the field, then you will get the initial linear relationship. So, for that part what we can write is V d is proportional to xi, and for higher xi the linearity is not followed, okay. So, it will help you understand, or you make one-to-one correspondence if you think of the stress strain curve. So, for reasonable field strength, okay, what we can write, that this V d is some kind of constant into xi, okay. So, V d for electron is some kind of constant into xi, okay, and this constant is called mobility, and its and material property. Okay. It is just like elasticity as you encounter in stress strain curve. Okay. So, this mobility is electron mobility. So, similarly for holes you can write mobility for the holes multiplied by the xi or the field strength. Okay. So, again this is mobility for and of course, the mu n and mu p will not be equal. Okay. For any material it will be different because they have different mass, they have different motion, okay, the collision and everything. So, mu n and mu p do not have to be equal. Usually mu n is greater than mu p. Okay. The mobility for electron is more because the effective mass of electrons is less. That is why the mobility is more for electrons. Now, if the doping level increases, that means collision with ionized dopant element that also increases, right, and it decreases the mobility. So, for a certain doping level you can define a mobility which is a material property. Now, if doping level changes, then the mobility can also change. So, now with the introduction of this mobility, what we can write, this J n drift, which is the electron density, the drift velocity induced current density due to electron only, we can write q n mu n xi, right. So, V d for electron we have replaced that with mu n and xi. So, here I should, for whenever we are using V d, we should use whether it is for electron or hole. So, here let me write it is for electron and for hole, okay, so that this mobility dependence is ensured. So, now V n we have replaced that with mu n and xi, and so J n drift will be like this, and similarly J p drift will be q p mu p psi. Okay. So, here one thing you note that in both the expressions q is common, right, because electron and hole they have equal amount of charge, they carry equal amount of charge, but the sign is opposite, electron is negative, hole is positive. Okay. And this P, so this P or the N just above it is the concentration of hole, okay, and this P is just the subscript P, P which is with the mobility symbol. Okay. So, please pay attention, q p mu p xi, that does not mean q, the first P is not a subscript, but the second one is. Okay. Now, the total current due to drift will be the summation of these two currents, right. So, total current density due to drift will be J drift will be equal to J n drift plus J p drift. is not it? Because both of them will carry charge, and that is why the total current density will be summation of them. So, rather we can write the J drift will be equal to q into n into mu n plus q into p into mu p multiplied by xi, and this whole thing we can write to be some conductivity sigma multiplied by xi, right. So, this is the definition of conductivity. Okay. So, the amount of field you are applying, whatever proportionality constant it has with the drift current is called the conductivity, okay. Or the same thing we can write as 1 over resistivity, okay. So, this rho is resistivity. So, now you know what is the source of this resistivity or conductivity. So, conductivity you can write in terms of q into n mu n plus p mu p, right. So, it is not a black box anymore, you know from where all these things are coming. Now, the other than the drift current, what we have is the diffusion driven motion or diffusion driven current. What do you mean by diffusion? Diffusion is a thing which is driven by the concentration gradient. Whenever you have a concentration gradient, it will diffuse to a portion where the concentration is less. Okay. So, whenever there is a concentration gradient, there will be a diffusion motion, is not it? It is not only for charged particles, it is for any particles. Okay. For charged particle also, if you have some electron concentration more somewhere, it will try to move or diffuse to the portion where electron concentration is less. So, that diffusion phenomena is driven by the Fick's law, okay, and the flux of electron is obtained with the the diffusion coefficient for the electron multiplied by the gradient in concentration, okay. So, this is what? This is the electron flux, okay. This is the diffusion coefficient, and this is the gradient in electron concentration, right. So, now if we have this diffusion driven current, what we can write is the electron or electron diffusion driven current density will be minus of q into phi of n, okay, because it will be carrying that much charge and the current density will be negative of that charge. So, if we put that phi value, we get q into dn, then gradient of the electron concentration. Similarly, the current density for hole diffusion will be minus q of dp dpx dx. Okay. So, here also you will see that this is the diffusion coefficient for hole. So, you can intuitively think of this, that the diffusion process will also be driven by similar things, right. So, electrons will try to go to lower concentration region, and in the path it will collide with the similar carriers and atoms as it does for a drift driven motion, is not it. So, there must be some relation between these two, diffusion driven motion and the drift driven motion or field driven motion. So, here let me write this observation or this intuitive question, which we will come back after discussing a little bit of other things. So, as the drift driven motion and diffusion driven motion go through the similar process of collision and deceleration, etc., they must be somehow related, right. And so, that means this mu n and d n should have some relationship, should be related, and similarly mu p and d p, is not it. So, we will come back. So, come back to this after we discuss, after we take a little detour, because we will need that detour to make this relationship possible. So, what is that detour? Now, we will come to two key concepts which are key to the photovoltaic effect. So, what are those two key concepts? One is called band bending. Okay. Band means the electronic band structure, it bends. Under what circumstances? We will see. So, that is one concept that you will require, and the second one is the constancy of the Fermi level. Earlier we have seen that to quantify the concentration of electrons and holes, we needed two key concepts. One was density of state and the other one was Fermi function. Here also, for going to the next level, to input the carrier motion, and that is how the photovoltaic effect is generated, we need to have these two key concepts. One is band bending and the other one is constancy of Fermi level. So, now we can think of first let us look at this band bending. Okay. Now, intuitively you can think of, for drift current we need a field, right, that we already talked about. It is a field driven current which is called drift current. Now, what is electric field? it is the negative gradient of electrostatic potential, right. So, that is the definition of electric field. So, you can write this I as a negative gradient of electrostatic potential. Here V is the voltage or potential and x is the distance. So, the xi initially we told that in the initial part up to 1000 volt per centimeter, right. So, that is the unit of field, volt per centimeter. Here also we can see that it is dV dx with a negative sign. So, that means physically that whenever we have a field, or we say that a field is applied, that means we have a gradient in potential. If the potential is flat, then we do not have a field. When the potential has a gradient, then only we can have a field. So, that means the band picture has to change, right, because band picture is what? It is the potential energy description of the electronic states, that is the band picture. So, whenever you have a potential gradient, it has to change. So, initially when you do not have any potential, or you do not have any potential gradient or a field, then we can write this to be conduction band and this to be valence band with flat potential. Okay. So, this is the case for xi equal to 0. So, if you have this datum, this reference level, okay, from this everywhere has the same height for the conduction band or valence band, okay, and that is why you do not have any gradient of it. Now, whenever we call xi is not 0, then that means it has to have some gradient. Now, everything is bent, okay, because now with respect to the same datum, if you say reference state or datum, now you have here EV is larger, EV1 is larger than another location where it is EV2. Similarly, here EC1 is greater than EC2, isn't it? So, this has to be the case when xi is non-zero. So, to get a field, to obtain a field, the band has to bend, right. That is the concept of band bending, which is called band bending under a field. Okay. So, now if we want to quantify that, so the potential energy is equal to minus q into V, that is the voltage for electrons, okay, and it is equal to q into V for holes. So, what we can write, xi is 1 over q d E c, E c is the the conduction band energy, that means for the electrons. Conduction band is associated with electrons and valence band is associated with holes. So, we can write xi to be 1 over q dEc by dx, and it is equal to 1 over q dEv by dx. Okay. And everywhere you will see that both the conduction band and the valence band will be affected equally, and that is why they stay parallel. Here they are parallel as this dEc dx is equal to dEv dx everywhere. Okay. And that is why they stay parallel, but the overall band bends. Now, the second concept we are going to look at is the constancy of Fermi level. Now, what is Fermi function? Fermi function is the probability of finding an electron at certain energy state E, right. So, Fermi function Fe is the probability of finding an electron in the in the energy level E, okay, or an electronic state at energy level E, whether it will be occupied or not, that probability is represented by the Fermi function, right. So, and Fermi level is what? Level is the energy E for which this probability is half, right. So, it is one point on that Fermi function, a particular value of that Fermi function, which we call Fermi level. So, it is important to think of this physical meaning, because otherwise you can mathematically juggle many things, but the fundamental idea or concept will never be clear. So, please pay attention that why the Fermi level has to be constant, the constancy of Fermi level principle based on this physical concept, that it is the probability. So, what you can write? So, in a single semiconductor material under equilibrium, okay, the probability of finding an electron at certain E cannot change, right. So, that means the Fermi level has to be constant throughout the semiconductor material under equilibrium. So, if the probability changes, then there will be some motion, and under equilibrium that motion is not allowed, right. So, that means under equilibrium the Fermi level has to be constant everywhere. So, what it means? That E dEf dx will be 0, because if that is not the case, so this is called the principle of negation. Okay. If it is not the case, there will be preferential movement of electrons which violates the condition of equilibrium, right. So, you start with some hypothesis, okay, if this is true, and then you end up with something which is unphysical or not possible. Then you say, okay, the first thing we have assumed that cannot be true. This is how the principle of negation or the argument of negation works, and that what tells us that constancy of Fermi level has to be maintained. Now, so we talked about that we will come back to this motion, we have to connect this diffusion coefficient and the mobility of that material or mobility of electron in that material, we will connect them after taking the detour. So, now we have talked about the band bending as well as constancy of Fermi level. Now, we are coming back to the motion again. So, if we look at the combined drift and diffusion motion, okay, then what we have, this total current density due to electron will be current density due to drift plus current density of electron due to diffusion, right. And we have also quantified them at least in terms of this mobility and diffusion coefficient, that it is q into n into mu n xi plus q into capital D subscripted with n d nx dx, right. These two terms we obtained earlier, and for hole Jp, the current density due to hole, it will be again due to drift plus diffusion of holes, okay. And here what we have is q into p mu subscripted p xi minus q capital D subscripted p d px dx, right. And the total current or total current density, we can write J will be Jn plus Jp. We can write Jn plus Jp because in the original current density itself we have taken care of the direction. So, the electrons go in opposite direction to the current and holes go in the opposite in the same direction to the current. So, that is already incorporated in these expressions. So, here we can write it is just simple addition. Now, under equilibrium condition there should not be any net motion, isn't it. So, we can write J n will be 0, okay. No electron should in effective way move. So, that means J n drift has to be equal to minus J n diffusion, okay. And similarly holes will also should not have any effective motion or net motion. So, this will tell that J p drift will be equal to minus J p diffusion, okay. Now, we are in a position to connect these two, the diffusion coefficient and mobility. So, for equilibrium condition we can now connect, because you can see that on the left hand side you have this mu and on the right hand side you have capital D or diffusion coefficient. Okay. So, under equilibrium condition we can now connect this mu and D with the help of the two concepts that we have introduced. One is band bending and the constancy of Fermi level. Okay. How can we do that? Let us see. So, for or from constancy of Fermi level and some generated field, what we can write, and it has some generated field, but still under equilibrium. So, net motion will be 0, but it has some field. If there is no field, the drift motion will be 0, and if drift motion is 0, then you know that the diffusion motion will also be 0 under equilibrium. But here at equilibrium you have some field and the equilibrium is also maintained. So, the two currents has to cancel each other. So, in this case what we have, that due to generated field we have this band bending. So, let us say this is the change in potential for the conduction band, and this is the change in potential in the valence band, and we have seen that they will be parallel because they are measured under the same datum. And constancy of Fermi level says that throughout the material the Fermi level should stay the same. Okay. It cannot be different. Now, we can also draw the intrinsic Fermi level here. Intrinsic Fermi level is where it is exactly in between the conduction band and the valence band, right. So, this is the intrinsic Fermi level EI, and this particular thing is our actual Fermi level under the equilibrium and under a certain field. So, let me write that EF is the Fermi level of the doped semiconductor okay, and EI intrinsic Fermi level, which is in between EC and EV, or rather which is halfway in between. It is exactly bisecting the EC and EV. Okay. But EF, it can have different distance from the EC or EV depending on the doping level, right. So, that is why we have kept EF to be the doped semiconductor or extrinsic semiconductor Fermi level, but it has to be constant throughout. Now, depending on the distance between the conduction band edge and the Fermi level, the electron concentration will change, right. This we have seen earlier Okay. How the distance between the Fermi level and the conduction band edge, I mean it is, you can quantitatively relate it with the electron density, and similarly the distance between the Fermi level and the valence band edge, you can relate it to the concentration of hole. Okay. So, in this case, in the above figure, you can write the concentration of electron with the distance will be somewhat like this. It will increase as you go up in x. So, let us say this is x. Okay. So, as the distance between EC and EF is decreasing with x, so the electron concentration will increase with x. Okay. So, this we have seen earlier, we are just making connection between these two. Now, this EC and EF, or the distance between EC and EF is related to distance between EI and EF, right. You can see it here that you can also write it terms of EC minus or EF minus EI. So, what you can write, this Nx will be Ni multiplied by exponential EF minus EI divided by kT. So, this is nothing we have done, we have just used the formula that we earlier derived in the last class, that the concentration of electron will depend on the distance between the intrinsic Fermi level and extrinsic Fermi level, and the Ni is the pre-exponential factor, which is the intrinsic concentration of electron. Okay. So, if this is the case, now if we apply the equilibrium condition, that means the effective flow of electron will be 0, we can write q n mu n xi plus q dn dn x dx will be equal to 0. So, that means dnx dx is, now I mean it is not related. Now, this one is, we can write EF minus EI by kT. So, this is minus q by kT into n xi, as xi we have defined it to be like this. Okay. So, from here if you put this information here in this expression, what you get is dn by mu n is equal to kT by q. That is what we were after, right. So, we had to relate the diffusion coefficient and the mobility dn and mu n, and they are related this way. Okay. And this is famous Einstein relationship. Okay. So, we will elaborate on this in the next class, and we will go further in the motion of these electrons and holes. Thank you for your attention. We will see you in the next class.